In this video, we present our IROS 2023 submission titled Task-Oriented Grasp Prediction with Visual Language Inputs. We first briefly talk about the motivation of this work. To perform household tasks, assistive robots receive commands in the form of user language instructions for tool manipulation. The initial stage involves selecting the intended tool and grasping it in a task-oriented manner. This requires the robot to comprehend not only what object to grasp, but also how to grasp in a manner that enables successful task execution. However, previous studies on visual language grasping have primarily focused on the formal problem of what to grasp, namely object grounding, while overlooking the latter issue of how to grasp, namely task grounding. Task-incompatible grasping can potentially hinder the success of subsequent manipulation steps, thereby highlighting the significance of addressing this issue. In this slide, a man is preparing food with a knife in the kitchen. We humans perform different task-oriented grasps in response to different task instructions, even on the same object. So, how can we endow robots with the same ability to predict task-oriented grasps in the context of visual language grasping? To answer this question, we propose GrassClip, which addresses the challenge of task grounding in addition to object grounding to enable task-oriented grasp prediction with visual language inputs. To specifically evaluate the task-oriented grasp prediction performance, we provide a costume dataset comprising 28 object categories, 96 instances, 38 household tasks, and template-based language instructions. A system is also built to enable an assistive robotic arm to predict and execute task-oriented grasps guided by user language instructions. Next, we delineate our proposed methodology. After perceiving the environment, GrassClip receives two types of inputs, a visual scene observation and a natural language instruction. We utilize two clip retrained encoders to encode multimodal inputs into a joint representation space, which enables cross-modal reasoning and semantic understanding. Then, a two-stage task-oriented fusion module progresses from coarse to fine. The TOF module includes a coarse-grained object grounding module and a fine-grained affordance grounding module. This is in contrast to previous works which have focused on object grounding only. The decoder predicts task-oriented grasp poses based on instruction conditional representations generated from the previous stage. Specifically, the COG module coarsely grounds the entire sentence to the target object. An FBG module utilizes self-attention mechanism to explore the affordance regions on the target object, and a cross-attention mechanism to establish fine-grained correspondences between the affordance regions and word tokens, especially task and object tokens. The structure of each component is provided in this slide. To showcase the practicality of GrassClip, we integrate the algorithm into a 7-degree of freedom assistive robotic arm platform to grasp previously unseen kitchen tool objects. The robotic arm is equipped with sensors that gather multimodal data, which is further processed by GrassClip to generate task-oriented grasp predictions. Subsequently, the robot executes the predicted grasps. Next, we provide an overview of the data generation pipeline. The data generation pipeline can be divided into 8 steps. First, a collection of objects and tasks are selected. Second, for each single object, the human operator teleoperates the robot arm to multiple stable grasp poses in the Cartesian space and assign task labels. We empirically found that our method is sensitive to viewpoint change. Therefore, we collect multiple views for each object. Fourth, the collected grasp poses in the Cartesian space are back projected to the image space with an extrinsically calibrated camera. Single object mask is then segmented from the background. To densify sparse human annotations, we interpolate between two annotated samples for a designated task in the fifth step. 6. We sample single object data with random translations and rotations to form a multi-object visual scene observation. In the seventh step, a target object-task pair is selected to produce a template natural language task instruction. Last, grasps satisfying the task instruction are preserved and transformed to form the ground truth grasp set. Here, we provide the full object set and task set used in the creation of our costume dataset. Here is a pseudocode for data generation. Finally, we present real-world robot demos to showcase the effectiveness of GrassClip. That's all for our video. Thanks for watching.